Imagine a high-end drone locked perfectly in midair. Its motors are constantly making tiny adjustments, processing sensor data hundreds of times a second to keep it perfectly stable against the wind. Now, let's try a thought experiment. What if we instantly pulled one invisible internal component from its circuitry? We're going to leave the battery fully charged and let electricity flow through the board at 100%. The drone immediately drops out of the sky, plummeting towards the ground. The entire stabilization system crashes instantly. We usually think of electricity as the only thing keeping electronics alive. The assumption is that if a device has power, it should work. But this failure shows that raw voltage isn't enough. Without a specific mechanism to coordinate that energy, the machine can't actually process information or execute a single command.
To find that missing piece, we have to look deep inside the device, right down to the silicon of its STM32 microcontroller. The missing element is the microcontroller's clock, which provides a continuous electrical pulse that dictates the timing of every internal operation. That pulse is the true vital sign of the hardware. Without it, a fully powered computer is essentially a useless brick. At a mechanical level, a clock is just a periodic digital signal. This signal rhythmically alternates between high and low voltage states. We measure this in hertz, cycles per second. An embedded clock scales from 1 kilohertz up to 100 megahertz. The faster the pulse, the faster the processor executes instructions and moves data. Every single operation a CPU performs depends entirely on the exact timing of those electrical transitions. This diagram illustrates the inside of an STM32 chip. It acts like a crowded city made up of separate hardware modules that constantly share resources. You have timers measuring delays, memory banks storing variables, and communication lines moving data. Operating independently without a shared timing reference results in chaos. Data collides, and the system crashes. The clock signal acts as a universal synchronizer, distributing a single pulse to every module. Now there is strict order. On every pulse, all subsystems step in perfect unison. This timing signal is the mechanism that allows these independent hardware blocks to function as a single coordinated system. Going back to our plummeting drone, we can now see exactly what went wrong when we removed the clock. This graphic shows the exact moment of failure. When that square wave flatlines, the CPU instantly loses its cue to fetch the next instruction. From there, errors cascade. Timers stop counting, motor control signals vanish, sensor conversions halt completely. The battery is still delivering full electrical power to the chip, but the synchronization required to actually utilize that power is gone. Without its timing reference, the microcontroller is paralyzed, trapped in a state of suspended animation. This is why engineers universally refer to the clock as the heartbeat of an embedded system. Whether building a smart home controller, an industrial robot, or a drone, reliable performance depends entirely on a properly configured clock. Writing flawless code and providing clean power are important, but they aren't enough on their own. Mastering time inside the chip is the required first step to mastering embedded systems.